So now I want to do a few case studies, okay, to make this logistic regression even clearer, so that you really understand its behavior, its benefits, and its limitations. This is a web page I found on the internet where someone is asking whether logistic regression is better than linear regression. Something that you will normally do, okay? When you have a homework problem, you will go to Quora and then you type something, or MathStack, you will type something, right? So you type a question and then some genius, they will respond, and then they will give you an answer. And so this is one of the examples I got from the internet. Okay. So the person who asked the question is this. They ask, is logistic regression better than linear regression? And then they answer, the guy who responds says that, logistic regression, on the other hand, can handle this outlier with no issue. Okay. So you can see that I'm skipping the discussion before and after. The problem is this. You have the blue circle here, and then you have the red circle here. If you try to use the linear regression model, it will fit pretty well here. Okay, you will fit somewhere here, and then you will miss the outlier. The outlier is going to affect your linear regression a lot. Okay? And then if you use a logistic regression, it seems like that when you try to fit this data point, the logistic is fitting pretty well. Okay, so that's the argument that logistic seems to buy you some benefit in terms of fitting the data. So we can ask, is this a really true argument? So we can do some case study and see if this argument works. Here is a few examples that I run on my computer. So first of all, let's construct two classes. Okay, before I answer that question, I'm going to show you some case studies. So you construct some data points. The two Gaussians, they have indeed the same covariance matrices, and then they have the same prior. Okay, so it's half and half. Half of chance getting this, half the chance getting the other one. And then you have a lot of samples. So on this plot, you have a lot of numbers. You have the blue crosses, so they are the true samples. And then the circles, they are the training samples. Of course, training set is a smaller set of the true samples. So you have all these samples. And then the green is the Bayesian oracle. Because I know my distribution, so I use my Bayesian equations. I know the center, I know the covariance, so I can calculate the Bayesian oracle. The black line is the Bayesian empirical. Bayesian empirical means that I look at my data points, I look at my orange data points, I calculate the mean, I calculate the covariance, and then I estimate them. So I have an estimated line. Now, in this case, the black line is pretty close to the green line. So that means your estimated Bayesian is pretty close to the oracle. Then I do what? And then I do this linear regression. Okay, so I just fit the orange circles using my linear regression line. And then I use this blue line, which is the logistic regression line. Okay, then I fit them, and then I set a cutoff at 0.5, so I get the red dotted lines, and then I get the blue dotted lines. So these are my decision rules. Alright, so these are all the legends on this plot. Okay, so now you observe one very interesting thing. First of all, my linear regression line is here. Does it fit well to my data? No. Well, okay. You have so many data points that are so far away from your linear regression model. I just cannot say that it's fitting well. Okay. And then my logistic regression fits very well. Okay. To my data points. However, that's just the training phase. Right? Remember, there's a training phase, there's a testing phase. In the training phase, you're going to use the orange dots to construct the line. In the testing phase, what you're going to do is that you put a threshold, and then you get a decision rule, and then you test the testing samples. Now, what are the testing samples? It will be all these blue crosses. Okay? Now, because I have this linear regression model, I have a threshold, the actual decision rule returned by my linear regression model is this dotted line. I test it on my blue crosses. It's no worse than my logistic regression line. So the feeling that you are obtaining, the good-looking feeling, okay? So I really want to make it clear. That makes you feel happy, okay? That you feel like, okay, I'm feeling very, very well. That's only making you feel happy because you're feeling well in the training phase, okay? It doesn't really mean much when you go to the testing phase, because in the testing phase, you're setting a threshold there, okay? And so even a linear regression model is not going to hurt you much. Now, of course, what would be the difference is that your training loss, okay, for the logistic regression would be a lot smaller than the training loss of your linear regression model. However, having a lower training loss does not mean that you will have a lower testing loss, right? Testing loss means that you need to use the testing samples. Training loss says that I only want to make my training sample happy. Okay? And for the linear regression case, the linear regression, if you use it for classifier, there's indeed a two-stage process. You first find the discriminant function, which doesn't really fit well to my data. However, the classifier itself, if we put in a threshold, that can fit well to the data. Okay? So that shows you some difference between the linear and the logistic. Indeed, there's not much difference in terms of testing. Now, let's look at the second case. Again, I'm assuming that we have identity covariance, okay, identical covariance. And then we assume that we have equal prior distributions. Okay, so same setting as before. But in this case, I am assuming that we do not have a lot of training samples. So what do I mean? Well, you have all these blue crosses, okay? And then these blue crosses, they're the true samples, but you only have a few of these orange circles. So you have a very little amount of training samples, both here and there. For this particular example, we have drawn the Bayesian oracle, and interestingly, the Bayesian empirical is pretty good. Now, this is not always the case because you only have a finite number of samples, and so the Bayesian empirical is not always as good as the oracle. Let us look at the linear regression, and also let's look at the logistic regression. If you look at the linear regression, you're trying to fit all these orange circles, and because they're located pretty far apart. And so the fitting, again, is pretty bad if you look at the training loss. If you look at the training loss of the logistic regression, you look at this logistic regression line. Does it fit well? Wow, it fits almost perfectly well on this data set. Why? Well, it's because you don't have enough samples. When you don't have enough samples, you just find a line that can just make everyone happy. Okay? Of course, when you have a lot of data points, you're not able to make everyone happy. But if you have only a few data points, your logistic loss will be almost zero. It will be very, very good. Okay? However, if you look at the testing error, the testing error is what? Where you set a threshold, and then you look at the blue crosses. Who's making more error? Well, you see how many blue crosses have been made mistake, right? So here are all the blue crosses that you will declare a wrong class. Another way to compare this is that you look at the Bayesian oracle, you see how far you are from the Bayesian oracle, and you realize that the linear regression case and the logistic regression case, they're as bad as each other. There's really no clear benefits. Let us look at another case. All right. This case says that we have two different covariance matrices. Then the Bayesian oracle, by definition, you have different covariance matrices. You should have a quadratic classifier. So that's the green line. And then if you run the Bayesian empirical, because of all these data points, you will be able to get this a pretty good curve. Okay. Now, you run the you run the linear regression model, and then you run the logistic regression model. Again, in this case, your logistic regression fits pretty well, and you realize that the training loss is not too big. Okay, of course, you have a few data points that you have missed. Okay, like this one is not exactly a zero, but overall it's pretty good fitting to the data to the training set. When you look at the decision boundary, I wouldn't say that this logistic regression model is significantly better than the linear regression model because they both cannot capture this green curve shape, which is a quadratic behavior. Okay, so I would say that they're equally bad. They're fundamentally first-order methods. How can you handle second-order properties? Okay, so there is no advantage from this perspective of handling higher-order issues. Now, the last example is this. You have identical covariance, but then you have unequal prior, meaning that here you have more samples, and then here you have less samples. Okay, so that's the underlying distribution. Now, you run the Bayesian oracle, you get a green line, and then Bayesian empirical, you get a black line, and then you run linear regression, logistic regression. Again, there is not much difference. All right? Okay, so to this point, we can go back to the question that I asked you in the beginning. Is this really a benefit of the logistic regression? The answer is no, right? Because by fitting this outlier well, you're just making the training set happy. That doesn't really buy you much in terms of the testing loss. You just don't know. Okay? If I run a linear regression to this case, as I have shown here, even you have outliers somewhere here and there, unless this outlier is really far away, right? Otherwise, this linear regression and also this logistic regression, they seem to perform equally well. And to justify this, what you want to do is really to look at the Bayesian oracle, because without the Bayesian oracle, you don't know what is the ground truth classifier that you should aim for. Okay? You cannot arbitrarily just allocate one point here and say, hi, okay, here's an outlier. The chance of getting that outlier could be very small. Right? So, the clear benefit between logistic versus linear, to me, is not that obvious. Okay? So what can we conclude about this comparison is that what logistic is really buying you is the probabilistic interpretation. That's the only thing that it offers you. Does it really buy you better performance? According to these 4 case studies, it does not appear so. Okay? But why do we want to use logistic regression more often than the linear regression? Well, the reason lies behind that. One, normally you are working on classification, 2 classes, and logistic regression has this probabilistic meaning being 0 class or 1 class that has a more meaningful interpretation than a linear regression line. So there's a pretty good reason to use a logistic. 2, logistic regression, although it's a little bit more complicated, it's still convex. You can still minimize. You can still run gradient descent. It's still not too horrible to run. And so you can use that. And 3, this logistic regression, when you put a soft decision rule, it has some good connectivity with the Bayesian, with the neural network that we are very interested in. And so by studying this logistic regression, we can perhaps get some ideas of the neural network. Okay? So to me, the difference between the linear and the logistic, I don't see it very different. Okay? But because of the classification we are working on, therefore, it might be easier to choose a logistic regression because it is indeed doing this classification task than the linear regression, which tries to do the estimation problem. Okay, so here is some readings, same set of readings as last time, which I encourage everyone to take a look. And this is the machine learning perspective. This is the statistics perspective, depending on which community you are from. And they are both very related to what we are talking about today. Okay, so I will see you next time.